Hello. Okay, everybody, I'm here to talk about succinct proofs in Ethereum. So it's a little bit different than what Benedict thought it was. I'm not going to talk about specifically implementing cryptography inside the EVM, but what I'm going to talk about is two things. So using ZK proofs for privacy in Ethereum and using ZK proofs for scalability. Okay, so first just a little bit of introduction, just in case people aren't aware of what Ethereum is and different things like that. So Ethereum is like the second biggest cryptocurrency. It has smart contract functionality, which Benedict used in his Zether. So the idea is that with Bitcoin you can send money from one person to another, but with Ethereum you can have like more complicated rules about how you send money. So we can use these complicated rules to make different things. Okay, so Ethereum supports snarks, bulletproofs, and stacks, and also Sigma protocols and a bunch of other things, because you can do like general cryptography in the EVM. You can do a bunch of cool things, but it's pretty expensive to do that. So then some limitations. Ethereum is limited to about 15 transactions per second, and every transaction in Ethereum is completely transparent. So there's no privacy at all. So Ethereum also has the largest development community in the cryptocurrency space, I think. And so because of that, we're passionate about putting the tools to do ZK proofs into as many developer hands as possible, because the Ethereum community has been about this programmability for a long time. We really want to empower developers to build things with it. So ZK proofs have been around in Ethereum for about almost 2 years now. And there's 3 languages that exist at the moment. So from high level to low level, we have Zocrates. Zocrates is a high level language. And if you notice the first talk or the second talk today, they use Zocrates. So one of the good things about Zocrates is that it has this kind of interface that developers are kind of used to. Yeah, you have for loops and things like that. You don't have to go down to the rank 1 constraint system level that Isaac was talking about earlier that can be kind of messy. So that's the highest level language that we have. And then there's Circom by the people from ID3. And Circom is a little bit lower level. They use this paradigm of having like signals and wires in order to build in order to allow developers to build things without having to go as low as you have to go with Bellman or with Circom or with snarks. So, and snarks is the third one, which supports multiple domain-specific languages, and that's the kind of lowest level one that I'm aware of at the moment. Okay, cool. Let's go. Okay, so what have we used zero-knowledge proofs for in Ethereum? So there's 2 major things that we're interested in doing with them. The first thing is privacy, and the second thing is scalability. So first, privacy. We have. So Miximus is a token mixer where you deposit 1 Ether and you withdraw 1 Ether, and you can't link the deposit to the withdrawal. Semaphore is like an expansion of this idea, but instead of having coins that you deposit, you can use reputation and make like generic signals about things. So you can do votes. You can do signaling, you can do like an anonymous social media thing, you can do a bunch of cool stuff with it. Then ID3, which Jordy talked about earlier, they do like a more flexible way to signal in with zero knowledge. And then the Republic protocol, which they have an MPC, so they have a dark pool. So people have talked today about having transactional privacy, but they have like trading privacy. So you can put an order in the order book and have that order executed without revealing what that order is. So that's Republic protocol, and they use MPC. And I just wanted to say that because I think people here are interested in MPCs as well, and there hasn't been a lot of talk about it recently. Okay, so anyway, then that's the privacy stuff, and I'll talk about that first. And then the second thing that I'll talk about is scalability. So this is where we use, so the verification of snarks and zero-knowledge proofs is shorter than doing the verification of everything. So the verification of snarks is succinct. So if we were to compress, so what we can do is we can push a lot of computations inside a snark and then just verify the snark succinctly. So we have, so we're really interested in this idea. We have like the people from Matter Labs are working on an implementation in Bellman. And there's also an implementation in Circum and maybe one in Zocrates that's in progress at the moment. Also, I want to mention a collaboration between 0x and Starkware to do something similar with Starks instead of Snarks. Okay, so that's like a summary of kind of what's going on, although I should have included what Benedict talked about. That should have been in the privacy section here, and I'm sorry if I left other things out. And if people have other projects that they want me to include on my list, please let me know afterwards, and I'll put you in. Okay. Okay, so anyway, I'm going to slow it down a little bit, and maybe this will be a little bit boring for some of the people who've been through this before. So I apologize for that. So if you guys want to go asleep for a while, I'll tell you when to start paying attention again. Okay, so a succinct proof is just a way to prove that. Do I have a light here? Oh, cool. It's just a way to prove that you did a certain computation with a certain input and a certain output. Yeah. So you have this code here, which defines the computation that you want to do. You have certain inputs and certain outputs. Cool. So then we can prove that we did the computation in this way, and we can prove it much quicker than it would take to do the computation. Yeah. We have a really great speed up in the verification time. Okay. So then we can hide some of the inputs, or we can hide all the inputs, right? So this is what's cool. This is hiding the inputs is where we get the privacy from, and the succinct verification is where we get our scalability stuff from, scalability benefits. Okay, so here's what a Merkle tree is. So we have a set, let's say A, B, C, and D, and we want to aggregate the set into a single succinct name. So what we do is we hash A and B together, we hash C and D together, and then we hash A and B. And we hash the hash of A and B with the hash of B and C and D, and then we get this root. And root is like our name for our set. And we can use that to prove that something is part of the set. Sorry about that, everybody. That's just in case people don't understand. Okay. All right, cool. Okay, so let's think about what's the first most basic thing we can do. And it turns out the most basic thing we can do is once we have our Merkle tree, we can put this inside a snark. Yeah, and then we can hide the inputs to our snark, and we can prove that A, B, C, or D is in our tree without revealing that it's in our tree. Okay, which is kind of interesting, but not really yet. So let's add this extra thing to our tree. Okay, let's add this extra thing to our tree where we have this kind of public-private. Yeah, so each A, B, C, and D is an independent person, and each independent person that's their public key. A, B, C, and D. And each A, B, and C, and D has a private key associated with it, which is nullifier and secret for each one. And you hash nullifier and secret together, and you get B. And that's your private key, so you shouldn't share that with anybody. So what can we do with this? So let's put this all inside a Merkle tree now. And now we have it so that only B is able to make a proof that B is part of the tree. Yeah, so now it's starting to get cool that we have this secret information and only that person is able to make proofs about their leaf being in the tree. You're right? Because our snark requires them to have nullifier and secret and hash it together inside the snark. Okay? So, okay. Now things are starting to get interesting. So what we can do here is we can make a coin mixer where someone deposits a coin, they get to put a leaf into the tree, A, B, C, and D. Yeah? And they know the secret information, so they're able to prove that coin is in the tree. But that's it. They're able to prove that, but they're not able to prove anyone else's leaf is in the tree. Okay? So here's how it works. A user deposits either into the contract, and they get the right to put a leaf into the tree. Users can use a snark to prove that a leaf is in the Merkle tree. Users who prove this can withdraw a coin. And there's no way to link a deposit and withdrawal, right? So, but there's one problem with this. Does anybody know what the problem is? Double spend. The problem is double spend. Okay, so there's a double spend problem here. So how can we fix the double spend problem? We can fix the double spend problem by revealing the nullifier and then sort of saving that in the contract. And every time someone tries to do a withdrawal, we check the list of nullifiers to make sure this one hasn't been withdrawn already. Okay. So that's Miximus. That's how Miximus works. So it's just a deposit and a withdrawal. It's a simple application for zero-knowledge proofs, and it's kind of the most basic thing we could kind of think of to do. Okay, so that works. Okay, so let's take this another step. And instead of having coins going in and coins coming out, which is kind of feels a little bit boring sometimes, let's use it with something else, something like more contentious. So we can use it with reputation. And we say that instead of depositing one coin and withdrawing one coin, what we can do is we can make this tree, and we can say at the next ZKProof event, we can give one leaf in the tree to every single person here, and then all those people are able to signal about something. They're able to prove that they're in the tree. They can use it to go to the reception afterwards. At the door, they can prove that they're in the tree in order to get into the reception. Okay, but that's kind of cool, but let's expand it a little bit. So we can just prove that you're members of the tree. You can't really say anything about being a member of the tree yet. So what we can do is we can add this idea of a signal. Yeah? So this is just a public input that you pass to the snark, and you can use the public input to say, I think that we should standardize X. Yeah? You can use it to talk about things. So you can say anonymously that something about what you're saying. But there is a problem with this. Does anybody know what this problem is? Okay, so the problem with this is that you can't double signal. You can't say, oh, I think we should standardize X, and I also think that standard Y is bad, because if you do both, your nullifier will be the same. Yeah, so you can tell that you can link those two signals together. So what do we do to fix this? Oops. Yeah, how do we fix this? Okay, what we do is we add this like external nullifier. Oh, but I took that out and I replaced it with signal. So what we do is we just hash the signal and the nullifier together. So now for every unique signal, we have a unique nullifier, but it depends on the signal. So you can do signal different things and have a different nullifier. So you can have this kind of privacy. So you can't link different signals together. So this is a kind of cool idea. And we could use it to do a whole bunch of things. We could use it to do anonymous voting and anonymous login. We could have a reputation system like this where you can risk reputation and lose it. And we have this kind of weird game that you have to play in order to sort of burn your reputation if you lose it. And then I had this cool idea to do like rate limiting. So if someone is messaging too quickly, there's a way that the snark will reveal what their private key is. Using like Shamir secret shares that's dependent upon the signal, which it's a cool idea, and I don't really have time to talk about it now, but afterwards if people have more questions about it, I can talk about it. Also, if I have extra time at the end, I can talk about that. Yeah, so that's the privacy stuff done. Okay, so now is the more interesting side of things, I think, or at least the side of things that people would be more interested in hearing now, because I don't know if people have talked about it so much before. So this is about scalability. So what tools have we had before? So before we had a Merkle tree, we had a hash function, and that was all that we really needed to do things. But this is a problem, because the person who's creating the snark is the person who has the permission to move those funds or to do that thing. But we want to remove this permission from the person who's creating the snark so that they can include more transactions, right? So what we do is we need to come up with a signature scheme. So very quickly, all the zero-knowledge proof systems that we use operate over a prime field, and it turns out we can make an elliptic curve that works over the specific prime field, and we can use this to make, yeah. So the elliptic curve that we generate will be specific to the zero-knowledge proof system that we use, which means that it has to be defined per zero-knowledge proof system, which is bad. So on Friday, we're going to talk about a generic way to do this. It's a workshop to come up with like a deterministic way to generate elliptic curves so that it's independent of, so it's easier. There's not all this overhead. Because, for example, Zcash did this for sapling. They came up with their curve jub. And then because they use BLS 381, in Zcash, but in Ethereum we use BLS 255 or 128, depending on which way you want to call it. We had to do a different curve, which was all this overhead, and it means we had to fork their tools and update the way their constraint system work and stuff like that, which is really annoying. But anyway, so that's what the talk on Friday is about. Okay, so come along on Friday and we can talk more about that. Okay, so anyway, here's the sort of the meat of what we're going to talk about now. Okay, so let's change our Merkle tree that we had before. So A, B, C, and D used to be individual people, but now A, B, C, and D becomes this account balance model, yeah, where every account has a certain number of tokens, where the owner of the account is defined by the public key, and the number of tokens, say, is defined here by the object. Okay? So, okay. So here's the new paradigm that we have. Okay? So we have the users who have this public key, and they also have the private key that's associated with this public key. So what we do is that if a user wants to send some funds, what they do is they create a signature and they sign their current leaf B hashed with the new leaf that they want to put there E. Okay? So when I said that this object was a token, let's say it's not a token because that kind of breaks things a little bit. But let's say it's just like a generic database where it's my public key and a list of my tweets. Say, okay, I'll add the token thing in a while. Okay. So now we have public key list of tweets. So I'm able to update this list of tweets to anything I want because it's my Twitter account and it's on the blockchain. So I should be able to update it to wherever I want. But a whole bunch of other people want to update their tweets as well, right? And normally, if we did this on Ethereum, it wouldn't really work out very well because it would be very expensive, number one, for people to update. And it would be very expensive for people to update. And it would also, so it would just be really expensive. Okay, so what we do is we have this, so every user creates a signature of B to E, where B to E is the transition that they want to perform. They want to go from state B to state E. Yeah? So what they do is they give this to the operator, and the operator includes this, as well as a bunch of other transactions inside a snark. And the snark creates a proof that checks the following things. Okay? So it checks the signature, matches the public key in the leaf B. Yeah? It checks that the leaf B is in the Merkle tree at state 1. Then it replaces leaf B with leaf E, and it recalculates the Merkle root. And that's it. Then we create our snark, and we have a proof that we can validate on the blockchain that the single state transition is legal and correct. Okay? And that's okay, so here's what happens. So then we broadcast it onto the chain, and look. We go from B to E. Okay? Okay, so this is kind of boring, right? Because it's only one transaction, and in theory, on Ethereum right now, it would cost much, much less to do a single transaction because it costs like 600,000 gas to validate a signature, and it costs like 22,000 gas to do a regular transaction. So why is this? Why are we really interested in this? And the reason is that we can include many, many, many signatures inside this because it takes about 100,000 constraints to validate a single state transition. And we can include 2 to the 26, 2 to the 27 constraints in our snark. So basically what we can do is we can just throw as many signature or state transitions into a snark and still pay the same cost. Because no matter how many constraints we include, the cost is the same. It's the same all the time. So when we do this, we can get like sub-cent transaction fees. Okay, cool. Okay, so here's just a little bit about what's happening in the smart contract at this time. So we have our state transition function, which is this snark that takes the old root and it has an output of the new root. Yeah, old Merkle root, new Merkle root, code, and the code is like the signature validations. Yeah, just validate this signature, this signature, this signature. No, well, it does the signature validations and it also does the state transitions. So it does the Merkle tree updates. Okay, cool. Okay, so, and then just to give a little bit more depth about what's going on here, is that we have a smart contract where people can deposit their Ether, and when they deposit their Ether, they can put a leaf into our Merkle tree, and then they can do two other things. The one thing is they can withdraw their tokens by doing a transfer to the 0 address. We have a 0 address in our Merkle tree, which is the leftmost address, and the balance, and tokens can go there, but they can't go out. That's one of the rules. Okay, because we put a private key there, or a public key there, and no one knows the private key too. Okay, so people can deposit their tokens there, and then they can withdraw them by sending them to the 0 address, and then we can use our zero knowledge proofs to do these transfers. Yeah, we can do zero knowledge proofs to batch transfers together. Okay, cool. Okay, so now we have one last problem. And our last problem is that we have a data availability problem. So the question is, this operator person who aggregates signatures together, they need to give everybody the data, the new data of the Merkle tree, right? Because, let me show you. Yeah.
Because in order to do a transfer, say something about E, you need to know what A is, because you need to be able to hash A and E together. So we need to be sure that the operator is publishing this data. Okay. So because if they don't do that, then they can just freeze everybody's money. They can't take anybody's money, but they can just freeze it, so it doesn't move anywhere. So what we do is that when they publish their proof on chain, we force them to give us a list of the differences between state 1 and state 2. So in state 1, which turns out to be just a list of the to, the from, and the amount of every transaction. I sent from my address, I sent either to Elaine's address, I sent 1 ether, and that's the list of things that is stored in the chain. Okay, so it turns out that because of these data availability guarantees, we can get between 100 and 500 transactions per second on Ethereum today with no changes. And that's about like 1 order of magnitude increase. Well, hopefully it could be a little bit more. Yeah. Okay, all right. Okay, so that's like the original idea for rollup. But this is a powerful idea. We can use this to do state transitions in a very cheap way, right? Because we only have to pay a single 600,000 gas, no matter how many transactions we include. So how do we leverage this to do more than just transfers and exchange? Because this is just an example. So it turns out that anyone can come along and define whatever their rules of transfers can be. Yeah, so people can come along and define other things. So you can look at this like another kind of smart contract language. That we have where the smart contract programmer would define their rules as a snark, the rules of their state transitions as a snark. Okay. Yeah, and this will let us build like highly scalable dApps. Yeah. So one thing that we want to do is make these tools more accessible to developers. And that's why we have a bunch of different implementations in Circom and Snarks and Bellman. To try and make it possible for other developers to kind of pick up and build whatever they want to build. Okay, cool. All right. Okay, so that's rollup. That's how rollup works. 3 minutes. Cool. Okay, so then there's a bunch of things we can do. Yeah. We can do. Yeah. So one thing we can do is we could validate bulletproofs inside the snark, because bulletproofs are validated over elliptic curve, which is kind of interesting because then we could do private transactions, and we could also possibly implement what Ben was talking about inside rollup, so that we could do confidential transactions inside rollup, and it should be super cheap to do, possibly. But anyway, I don't really have a lot of time, so maybe we can talk about that later if people are interested. Okay. Okay, so anyway, I have like 2 minutes, and let me try and say this quickly. So I think it would be a good. So this seems like a general problem that a bunch of different blockchain projects would want to do. And what I want to propose is that this would be a good way to compare different zero-knowledge proof systems, because we have snarks and starks and a whole bunch of other things, and we want to be able to compare them. So I think that what we should do is use rollup as like a general benchmark to compare different zero-knowledge proof systems. Okay. An example workflow would be like this, that we would build like a formal spec and an implementation in OR1CS. Yeah, and we would test it and audit it and everything, and then we would sort of encourage different academics who propose different zero-knowledge proof systems to implement, to use this rank 1 constraint system in order to use this rank 1 constraint system as a benchmark, and to give us the proving time, verification time, and things like that, and a number of transactions that they include. So we can figure out which ones are better and worse. And it's just a neutral way to compare different zero-knowledge proof systems, I think would be a good idea. Okay. Okay, so then we have a bunch of standardization stuff that we need to do. So the first step is to do the elliptic curve standardization. The second step is to standardize Pedersen commitments. And the reason why we can't do that first is because Pedersen commitments is specific to the elliptic curve, so we want to standardize the elliptic curve generation. Then we can standardize the Pedersen hash over a generic elliptic curve, and then we can do signature verification over a generic elliptic curve too. Okay. Okay, and then there's a bunch of stuff we can do with language standardizations. So I think it would be a good idea if the language exported, because a bunch of times in the language you want to do things about related to the prime field. And I think it would be good if our export formats for this would take that into account, so that when you export, you don't necessarily need to know what prime field you're going to be running your rank 1 constraint system over. I think that would be useful, because then we could implement things without having to worry about about what zero knowledge proof system it's going to be used in. Okay, cool. That's it. Questions? Thank you.